Okay, hello everyone. Welcome to the Multi-Agent Learning Seminar. Today we have Luke presenting. So Luke is a PhD candidate in computer science at Northeastern University. He's advised by Chris Amato. He completed his BS in informatics from UC Irvine. He also spent some time at Amazon Robotics working on simulation-free on-robot reinforcement learning. Luke's research interests lie in artificial intelligence, reinforcement learning, and multi-agent systems, particularly multi-agent exploration and cooperation in theoretical and real-world settings. He's seeking to develop algorithms that allow autonomous agents to learn to cooperate efficiently and optimally from their experience. So welcome, Luke. We're so happy to have you. And take it away when you're ready.
Thank you very much, Rivali, and thanks everybody for coming. So I'll just jump right in. If you guys have any questions, just write in the chat or just ask. So no need to wait. And today I'm going to talk about centralized critics. And centralized critics have been pretty popular nowadays. And a lot of methods developed on top of centralized critic. And we sort of look into what it does and sort of trying to theoretically understand more. And today I'd like to share some of that exploration. And this is joint work with Andrea, Yuchen, Brett, and of course, Chris. So let's see. Now we have centralized critics. Before we have centralized critics, we have actor-critic. Now we want to use actor-critic in multi-agent RL, and centralized critic was introduced. It sounds like such a great idea because we could have centralized training with decentralized execution. But something doesn't add up in our exploration. We found that sometimes centralized critic doesn't foster cooperation any better than decentralized critics. And there are some issues with biases. And if you only use state information in your centralized critic, what we call state-based centralized critic, and it actually, centralized critic can have more variance in policy gradient. We'll talk a little bit on why and how that's the case. In practice, centralized critic usually works pretty well. But if you just want to have one takeaway is that with centralized critic, you have less bias, more variance. Right? And with decentralized critic, you get more bias, less variance in your policy gradient. Let me briefly touch on what our setting is. We are operating in cooperative multi-agent reinforcement learning. So we're talking about Dec-GPs, where we have partial observability, and we don't get to observe the states. And we focusing on decentralized execution. So we have actors that are decentralized actors. But our critic, of course, can be centralized because we can train in a centralized way. And we have a centralized critic that could condition on history of all agents and sometimes the state, and we will mention that later. And we could have decentralized critic here as in a comparison because we could have each agent their own critic. So we classify the ideas into 4 different algorithms. If you take the actor-critic algorithm, they basically fall into these 4 categories. We could have completely decentralized critic. So for each of the actor, we have one critic associated with the actor. We could have different forms of centralized critics. Critic that maintains Q values for histories, and critics that maintain values for states. So we call state-based critics. And we have critics that maintain values for state history. This critic is more specific. We'll talk about that later. They all have different properties theoretically. So let me just dump all of the theory at you, and we'll talk about examples to better understand these things. So with fixed policies, the critics are able to converge to true expected return for basically any type of the critic. And we have theorems for history-based critics give same expected policy gradient. This is for history critic and state history-based critic. State-only critic, on the other hand, do not give you same expected policy gradient. This means that if history-based critic have the same policy gradient, that means for both centralized and decentralized history-based critics suffer the same cooperation issues. This might be surprising for people because we would assume that a centralized critic can help us solve the classical cooperation issues, but that's not the case here. And we'll see first thing why that's not the case. And because state-based critic do not give same expected policy gradient, so they can bias the policy gradient. And you don't have any guarantee where your policy will go or that they'll even converge. We'll first jump into an example where we see, okay, why some of the classical cooperation issues cannot be solved with a centralized critic. There's this game called Climb Game, matrix game showing the rewards for Alice and Bob. So matrix game, you can take one action, you get a reward, and there's no state associated with it. If we just apply the algorithm, we see something very important. JAC is, of course, a centralized actor-critic. You have one factor actor that is not able to execute in a decentralized way. So we see a centralized method that is able to give us the optimal value, which is taking the action of A1. And centralized critic and decentralized critic all stays pretty low in the 5, 6, 7 range. So why is that? Let's take a closer look. So if we assume uniform policy, then we learn some critic. And we could have a decentralized critic for Alice that looks like this. And we could have a centralized Q. You can see that if we have a centralized critic, we quickly learn the whole table. It's very easy for us to learn the whole table because there's no stochasticity. You get the value and remember the value, and that's it. But for decentralized critic, you had to do some aggregation. But after a few tries, you learn, okay, action 1 gives me negative values. Action 2 gives me pretty negative values. So I'm going to stick with action 3, which is 3.6, is not that negative. And this is where the cooperation issue arises, because if we want the agents to cooperate, and they want to take A1. But from a decentralized view, assuming we have uniform policy, of course, A1 does not seem very promising. On the other hand, if we look at the centralized Q value, centralized Q value just tell me straight out that if you want to, the best action will be A1. And people would assume, okay, a centralized critic is more specific and you can capture that relationship. Now, let's consider what happens when we do policy update for action 1. Right? With decentralized critic for Alice, no matter what action Bob take, the critic only looks at local action 1, and gives minus 6.3. The centralized critic looks at joint action, gives either 11, minus 3, and 0, depending on what action Bob takes, right? Since we have uniform policy for Bob, we get each of these 3 values 1/3 of the time. Now, if we see the expectation of the gradient is actually, in fact, same. the keyword is expectation of your gradient, right? You can't just, when on policy learning, not encounter the -30 scenario. And this problem is called action shadowing, because it was considered the -30 shadows the 11. And then, so I'm somewhat intuitively, centralized critic is not able to solve our cooperation issue for those decentralized actors, because of the gradient. So this leads us to some variance analysis. We actually find out that the variance for using history and state-based critic is greater than the variance, policy gradient variance, of using history-based critics. And that is actually greater than decentralized critics. To actually get into what happens and what makes a policy gradient variance, we further classified different types of variance. So we would have multi-action variance and multi-observation variance. And I'm just going to give an example for both of them. So very intuitive understanding, I hope. Multi-action variance, what we call MAV, can be shown in this like game called Morning Game that we invented, or we take inspiration from other people. So there's two agents, right? They want to make breakfast in the morning, and then they would either have agent 1 could either do pickles or cereal. Agent 2 could either do vodka and milk. And then in this simple environment, if we have a centralized critic, I think I have wrong values here. The centralized critic would how do I go back? Well, the centralized critic would be just 1, 0, 0, 3, and your decentralized critic will give you very simple values, right? Pickles is 1, 0 is 3, and vodka is 1, milk is 3. So we see that a decentralized critic is an aggregation of this full matrix. And we also have multi-observation variance. So this guess game here is a little more complex. So imagine Alice and Bob are in 2 different rooms, and they each observe a uniformly initialized blue or yellow color screen, right? And they have 2 buttons on their sides they can press. They're rewarded by 1 if they press the button with the color that matches the other person's observation. So that's pretty much a random thing. The decentralized critic will tell us our expected return is 0.5 no matter what. Because partial observability, we can't see the other person's screen. So we just have to give it a random try. The centralized critic down below, on the other hand, give us 1s and 0s precisely for each of the combined situation. And this is good, right? We know exactly what we'll get for each of the situation. But does that help us anyway? In this case, in this extreme case, this specification is not helpful because it aggregates 0.5 no matter what. But we get 1s and 0s. That means extra variance for your policy gradient. If we state with our local critic, we'll get 0.5, which is deterministic value every time we go to update our policy. So that's multi-observation variance. That's the variance coming from you have multiple observations in multi-agent system. So if we take 1 step back, we had this diagram shows whether inputs and outputs of each component is local or joint. Joint is fat arrow, local is short arrow, like thin arrow. We can see that centralized critic on the left learn completely in the joint action history space, right? And decentralized critic on the right receive signal from joint action history space, but have to marginalize it down to local values. The marginalization over other agents' histories and actions carried out by both methods, right? You have decentralized actors, but by different components. On the left, the marginalization burden is implicitly on the actors, right? When you have centralized critic, because the policy gradient process does the marginalization. This give actor learning more variance, and therefore it's harder for them to learn for the policy gradient step, as we have seen in the climb game. On the right, though, the decentralized critic is more difficult to learn because its learning target has more variant. Same logic here. But once you have the decentralized critic already marginalized out the values, the actual actor training is simplified because there's less variance. So they're equivalent in theory, so does one work better? The short answer is not really. So they're equivalent in theory, they're mostly equivalent in practice. But there's like one example where there's some difference. This example is called Dec-tiger. It's a classical game, but it's like harder than you think. So in this environment, you have two doors and two agents. You got a tiger and treasure behind doors, of course, just like your tiger problem. But because it's Dec-tiger, is two agents, of course. And you could listen, just like in the tiger game, and gather information, noisy information, where the tiger might be, and hopefully you guys open doors together. Now, if you guys open the tiger door together, you get punished less. So that's the point of doing this in a two-person fashion, right? And if they get the treasure door at the same time, you get more treasure. So if they individually open doors, they get less treasure or more punishment, respectively. So this is really encouraging them to open a certain door at the same time. Now, empirically, the decentralized critic usually finds an okay solution where they open door after 2 or 3 times of listening. But the centralized critic converges to just opening door simultaneously on their first step. Now, this is because you have high variance in your policy updates, but depending on your learning rate and other things, it's harder for the agent to retain a stable policy. And that makes it harder to coordinate that simultaneous door opening. Like, is it opening on step 2 or step 3? So in the end, the agents just resort to opening the door at the first time step without gathering any information, like no listening involved. And there are some other results in the paper if you're interested, but this is just one of them that I want to highlight. So just to recap, right? With centralized critic, we have less bias and more variance. And with decentralized critic, we have more bias and less variance. That is talking about the policy gradient part. And you might say, okay, yes, of course, decentralized critic themselves are harder to learn. We also recognize that. And there's also the added problem of how would you solve actually a cooperation problem? Now, this is not entirely solved. There's some work on how to solve it in a fully observable setting with multiple agents, but we haven't solved the cooperation problem in the learning case for in partially observable multi-agent setting. Like before I go on, any questions? I don't have the chat open, so let me. Okay, appears everybody understands it very well. Now let's go on to state versus history. So we all know that if we don't have fully observable, we need history. History is the action and observation you gathered in your episode. We could have conditioned our critic based on the history, or we can do that based on the state. So you get state value or history value. Actually, you can have history state value, which is very popular. A lot of the methods, they're actually state history values. A lot of the value decomposition methods. But in any case, the simplest two cases is that we know that state is compact and it's easy to learn. State value sounds very easy, but history sounds very complex. You could have potentially very long time horizon, or in implementation, very long traces. And then you have different observations from different agents. So people would think, okay, you would fare better if you just used states. But first thing, right, it's states actually give you more variance. But how that's the case? Let me jump to an example. This is all related to some aliasing problem. But let's start with example, right? So there's this domain called beverage domain. Beverage domain is a single agent example, but same intuition, like why state is bad. In beverage domain, agent is a barista, serves coffee or tea. Now the client who comes in either prefer coffee or tea is a random initial state. Client come in, probably want tea, if you ask me. Well, I actually have coffee and tea on my desk, but I'm not a usual client. Now this client wants tea or coffee, so it's uniformly random. If our barista serves correct drink, in this case coffee, the customer is happy and we get a tip, say $1 or +1. If we serve the wrong drink, we get a complaint, say, I don't know, -1. So now you're to update the policy. You look at the value from your critic, assuming the complaint is worth -$1 with history Q values. Say for action of serving coffee on empty history, we just get 0 because we serve like randomly. Now on the right side, with state values, we get 1 or -1 each half of the time, because condition on the real state, you know the outcome. This is very similar to the previous example we talked about. Being too specific make you more variance. In this case, we didn't need it to know for empty history what the actual true state is to know what the value of serving coffee is. Right? Comparatively, that's a lot more variance depending on the state. With history-based critic, you get history value directly. So you don't have to do implicitly a weighted average over them. That gives more variance. So let's go back to bias analysis for just a bit. Right? Before we did, we compared gradient for centralized and decentralized critic, and they have the same expected gradient. Slight differences in variances, but they have same expected gradient. Now, state critic does not have the same expected gradient. It has some bias, in other words. So this, I want to start with a quote. This quote I like. Placing a value on the reduction of certainty is the first step. For only when we know that what is worth to reduce uncertainty, we have a basis for allocating our resources. Right. So information should get values. That's something we all agree on. But if you just consider the state, you're ruling out the possibility of gathering information is worth something. And let's revisit our beverage domain. Now we make beverage more realistic. So now our barista can ask, right, whether the customer wants coffee or tea. And our customer can either say, okay, I want coffee or tea, right? Tea in this case. And then you serve the drink with that information. Much better, right? Interestingly, now the customer is erratic or is not happy. And only disclosing the true preferences, say 75% of the time. Just to mess with the agent, right? So it might be the case that agent has to ask multiple times until they get a consistent answer. Say, I don't know, 2 or 3 times in a row, just to make sure. Now, of course, let's say there's a small time penalty. Otherwise, we might be asking his preference forever every time you ask. But you still want to get a relatively good policy, right? Probably something like asking 2 times and 3 times and making sure. So we get a bunch of history values. Now the history values, if you look at them, let's say we have a relatively good policy, right? We look at the Q values for the asking action. Now, after the comma is asking action, we're just looking at the Q values for that. And we have different histories associated with that. And this one, we just ask once, and customer said T. And this time, and the second one, we get answer T 2 times. And this one, we get conflicting answers. In this case, our value should decrease, right? Because we now don't know what this customer actually wants, and potentially we would serve the wrong drink, or we need to ask more times. That is costly. And then the third history is getting 3 T's in a row. That's pretty sure that we'll serve T and get our reward. So we get pretty high dollar value here. Does that make sense? Right? Information is valuable. Now there's only 2 states, right? Our customers only want tea or coffee. Now, the state values are weighted sum of state history values. That is average return of all the situations you might encounter with that underlying state. Now, because our policy does not bias against either type of customer, the overall value of customer wanting tea or coffee will be the same. Now, pause here for a second and let's think. In order to solve this problem, we had to trade the time penalty for more information. So if we get a consistent answer for our client, we ought to increase our value estimate, and vice versa. So the value of having more information outweighs the time penalty. And with that in mind, let's say now you need to learn a policy based on those values. What do those values tell you? Right? The history value tells you that if you are confident of the true customer preference, you are to expect a higher return. That makes sense. The state value just tell you, no matter what you hear from the customer, at any point in time, how sure or unsure you are, the value does not change. So asking, no asking doesn't matter. Now imagine learning any meaningful policy from that. That will give you no direction for a policy gradient meaningfully. So philosophy aside, let's see some but performances. Now usually we find history state quite similar in performances because the underlying algorithm is pretty much the same, and sometimes state and history are in fact pretty similar. especially in some environments. History is just observation is generated from a subset of history, maybe an observation radius. So in format, they're quite similar, and in information they contain, they're quite similar. So usually we don't see too much pronounced performance differences. For a select set of domains, sometimes you get a little difference, but we typically don't see a lot of differences. It has to be very observation model being very peculiar. So another popular benchmark is, of course, SMAC. SMAC, I think people have a lot of like suggestions for SMAC, and this is not SMAC v2. And for SMAC, we typically see the state-based critic works quite well, and this is contrary to other domains where state critic doesn't usually do very well. And I think the reason why state-based critic do so well at SMAC is that they actually, the state is actually not biasing the actions completely. Oh, we have Rapali. Hi, Rapali.
Hey, wait, so I think I got confused on that part. So the history state critic has more information than the state critic.
That's true.
But it can perform worse than the state critic.
That's true.
Okay, so I'm guessing that's because of the variance.
That's because of the variance. Yes, it has the highest variance, but nevertheless, I should add that if you're trying something new, or if you're working on a new environment, or you're unsure which one of them is the best, always try state history-based critic. It usually, empirically, of course, works the best because it's not biased, so you wouldn't get weird policy gradient like we mentioned in the information gathering games like the Barista. And with training, it could learn to ignore meaningful information, non-meaningful information. Although it has more input and more complicated, but it usually works a lot better. Yeah.
Just to add to that, but that would also be like this, it would also require more like storing information, because like the history will keep on getting added as more time passes, and then but the state is just going to be the current state, or
yes, of course, if your history is a masked state or a subset of your state, then you, with certain observation radius, your history could be a sequence of state that is, yeah, sometimes SMAC is like that in a sense, because far away agents don't really impact your decision. So the history is pretty much as good as a state. So in this case, just getting the state is better because it's so much more compact.
Okay, makes sense.
Yes.
Thank you.
Yeah. So I think that's all I have for today. I went through the examples pretty fast, but if we're going to take something away, is it's not even who has more bias and who has less variance. It's just we have to be like cognizant of different type of critics exist out there, and they all have different properties. And with partial observability, you sort of need the history. Okay, so I'm just opening 2 more questions.
Well, yeah. If anybody has any questions, feel free to raise your hand. Yeah. Caleb.
Caleb.
Cool. Can you guys hear me?
Yes, I can.
Okay, cool. Thanks for the presentation. I was curious, did you use shared weights in any of the analysis for the critic, or like shared weights between the critics of the different agents?
Good point. Let's see if I can find the slide where I have different type of critics, right? So the short answer is I don't share weights for the experiment, and we had actors here. In our experiment, actors don't share weights, and the share weights also apply to critic in this case where you have a decentralized critic. And the answer is I don't share weights, but if you do share weights and the agents are homogeneous, it doesn't affect the other conclusions that we have. Is that what you're asking?
Yeah, that's essentially what I'm asking. Okay, cool, thanks.
Good question, thank you.
Yeah, I think that's about it for the questions. Well, would like to thank you so much, Luke. The presentation was very interesting. Thank you.
Thank you very much, everybody, and thanks everybody for listening.
Manfred, can you hear us?